Hey, all you cool cats and kittens. So today we're going to talk about population. So a population is one step up from an organism. So it's the same species in an area. And demography is a study of a population over time. And this includes categories um, and info about each individual and whole populations. We look at things like population density, and a population density is the amount of people per an area, or the amount of an individual per an area. So if you're looking at deer, there are 30 deer per acre, or there's 525 people per 10 square miles, or something like that. That's an example of population density. Dispersion is where in the area people are found. If they're in an urban area, or if they're in a rural area, or if the area has both of those in it, there'll be a lot more people in the urban area and a lot less people in the rural area. And then we have birth rate and death rate. So birth rate is not mortality, that's death rate. I put that in the wrong space. So essentially, birth rate is the amount of people born over the total population. And then death rate is the same, as it's the number of people dying over the number of total population. And then as you can see here, the growth rate is the birth rate minus the death rate. And it's pretty self-explanatory. It's a positive growth rate, so it's growing when there are more babies born than people dying. And that's pretty self-explanatory. So next we have in looking at individuals inside of a population, and there's a couple of things that we'll look at. We'll look at life expectancy, and that's males or females living to a certain amount of time, and that changes over time. The addition of healthcare really increased our life expectancy as humans. Um, and it doesn't change in extreme ways all the time. Like for humans, that changed in an extreme way, but um, the blue whale doesn't change for them very often. And so then we also look at immigration and emigration. And immigration is when someone moves into an area, and emigration or exit when someone moves out of an area of study. And those are really hard things to pin down um, for scientists, because you have to determine zones, and then you have to find a way to track individuals. So how do you track, a bunch of frogs that all look the same? It's more difficult to do that. And so distinguishing population numbers with the additions of immigration and emigration, it's difficult to do. So these are some of the factors that affect population growth. So the carrying capacity is um, the limit of how many people or individuals can live in an area. It's how much an area can hold of a certain population. So, your garden outside can only hold a certain number of plants before um, it overflows. It only has enough nutrients to provide life for the plants in your garden. There's only enough light in that area for a plant to be able to absorb, um, things like that. And um, those things that I just explained are limiting factors. And those limiting factors can either be density dependent or density independent. So density dependent, it's kind of hard to say, that impacts populations most when they're close to K, or carrying capacity. Carrying capacity can be abbreviated as K, and you'll see that a lot in graphs. Um, but if, say, you're in a crowded area, disease spreads a lot faster. And you're in a crowded area when things are closer to carrying capacity. And so that limiting factor of space is density dependent, because it depends on the density of that area. Now, density independent, they impact the population regardless about how big population is. So that's natural disasters, hurricanes. Hurricane doesn't hit our coast because there's a lot of people living in Wilmington. It just hits our coast because that's the path that it's taking. It's not it's not dependent on the amount of people. It just That's what happens in nature. And something else we want to talk about briefly is premature death due to a small population. And that can happen if a population is small and the gene pool is small. There can be inbreeding issues and then more mutations and premature death due to that small population. Um, so the next thing that I want to show you guys is growth models. So a linear model, which I'm sure you guys know of from math, is essentially just starting from the origin, it just gradually increases over time. And not a lot of times do actual growth models of individuals show this, but it's one of the things to mention. The two that we're going to really focus on are exponential growth and logistic growth. So in exponential growth, the limit does not exist. Um, it's rapid growth, it's limitless, and they can grow exponentially over time. And then logistic growth is essentially, if you look at it around halfway up of population size and down, they look the same. But when you add carrying capacity or K into the situation, which in all cases there is a carrying capacity, so you need to put that into consideration. But it goes up to that limit, and then it it just continues along that line and it evens out because it cannot, go over carrying capacity. Um, and some things to assume when looking at logistic growth and carrying capacity is usually constant. That's why you see it's a straight line. It's constant. It keeps going on forever. But things can happen like fires, deforestation, things that can impact where the carrying capacity is, and that can change. And it's hard to pin down because there's a lot of factors that play into carrying capacity. So lots of times for scientists, that can be difficult to pin down. So this is what growth models really look like in reality, like real populations. Like if you're looking at deer, like this is going to meet, very similar to what that looks like in actuality. Um, as you can see, if they're, start here and there's not many of them, over time, they realize, wow, there's a lot of food for me. There's a lot of space. I can have as many babies as I want. I can eat as much food as I want. And then suddenly they run out of space. They run out of those factors, of those supplies of things they need, and the population crashes. And then it crashes under the carrying capacity, and then they're like, oh my gosh, I have all these things again that I can eat and space that I can, reproduce and have more babies. And it grows again, and then, but not as high as the first time because there's less, um, they have a more understanding of where that limit is. Um, and then, it dips again. And then, as you can see, it just kind of evens out over time. And like I was talking about before, if there's things like deforestation, fires, they have to reestablish, the individuals in the area have to reestablish that, tapering off. They have to level up and down again and find again where the carrying capacity is. Um, Next, we're going to talk about age structure. So age structure models are graphical representations of age and gender for demographics, and they can be used to predict growth and decline of populations. So as you can see here, India is growing. There are more younger people in the population than there are inside the reproductive time frame. And so that's within this circle. And there are more babies being born than there are people birthing babies, essentially. So they will more than replace their parents within the next generation. and that will in turn yield more people. Um, and then looking at Japan's, um, it's a little bit different here because you can see there are more people than there are children. And so in general, there are less than 2 kids being born per family, per a couple being together. So they're not gonna replace the generation that was before them. And that can be a problem, um, sometimes because of, the, economic structure. There won't be people to replace jobs come when other people retire or pass away. Now I can look at the United States, which is a generally stable population. 2.5 kids and a dog, and a picket fence. That's the American dream. That's around where people live around. Like, um, most people have 2 kids. That's the average, and those 2 kids will then replace their parents come the next generation, and so on and so on. And so it's relatively stable. Like showing here with the circle, you can see that the ages and number of people of different ages are around the same up until they get past, the 60s and they start dying off more frequently. And so why does this matter? How does this apply to why do we care? So rapid growing populations can cause disease and famine. Cough, cough, corona. I mean, the more people that you have, the more likelihood that you're going to come into contact with people who might have certain diseases. There might be less food in the area, and so that might cause famine. Developing countries, which is 80% of our world population, they have less access to healthcare and birth control, and so they don't necessarily have the ability to plan out their families like we do in more developed countries, places like Europe, North America, and Australia. We have more access to healthcare, and so we're more able to plan out our families more accordingly. Um, and in that sense, so 80% of our world population is growing big time, like I showed you, um, with India. Like lots of 80% of our world is doing this. And that can cause a problem because, like I said, compare carrying capacity, it has a limit. There is a limit to how many people that there can be. And that can be a problem, um, if we run out of space, for people. And the world went from 1 billion 200 years ago to 7 billion now, and that's a big change. That's a lot of people in a short amount of time to grow. But the reason it's growing is because there's more healthcare and there's more reasons why that carrying capacity can go up because we're doing better about taking care of people, and there's more access to food and to supplies. Um, and so technology and industrials, they're all increasing. And so things can do better. And so we can do better and we can live longer and we can reproduce more. And thus it grows. Lots of scientists are debating, where our carrying capacity really is, as a human population. But that's essentially populations. And we're going to talk more about some graphs and things and models when it comes to populations, in synchronous work. So have a great day.